last time, I assume, I may be wrong there, I assume that you guys did not want to kind of compete in the feeding frenzy for your exams, you know, that's why I handed them out. But then it occurred to me that maybe you guys enjoy that feeding frenzy. So I have to ask, I mean, how many people want to give up the exams and alphabetically, nice, organized? How many people just like that free-for-all with sharp elbows? Organized? These are still alphabetical, so at the end of the lecture, if you haven't picked it up, please do. Okay, so let's pick up where we left off last time. Okay, so we talked about the fact that interstellar additions of all types are going to be faster when you have electron-based quantum groups attached to the carbonyl. And they're going to be slower when you have electron donating groups attached to the carbonyl. And the reason is twofold, and the two reasons track. So in other words, when you have an electron donating group attached to the carbonyl, it lowers the energy of the starting material, and it raises the energy for the second transition state. The transition state is involved in collapse of the tetrahedral intermediate. And so likewise, if you have electron withdrawing groups, the opposite is going to be true. And for the second step, it's really easy to see why, because if you have an electron withdrawing group attached to the carbonyl, that electron withdrawing group is going to be a good leaving group. And so the activation barrier for step 2 should be low. When we say higher and lower, remember, compared to what? So the point of reference is always going to be the estimate. So that's where we're going to start. So another way to look at this, of course, is just to look at the resonance stabilization of the starting material. And so an ester, for an ester group, this is less important than the corresponding resonance structure that you have for an amide, because here the positive charge is on oxygen, more electronegative. For the amide, that positive charge is on nitrogen, less electronegative. And so, and then we can carry it one step further and look at chloride. For chloride, this is completely unimportant. Okay, so you don't really have any of this because two reasons. Okay, two reasons because you placed a positive charge on chlorine, and also because the pi bonding between chlorine and carbon is going to be weak because the size of the orbitals. And so this is not going to be important, and therefore the acid chloride is not stabilized by resonance hardly at all. Okay, so furthermore, the starting material for the acid chloride is destabilized by electron withdrawing effect of chlorine. So chlorine is already pulling positive charge out of a positively charged carbon atom. And so for these reasons, that's not going to, that this carbonyl is reactive. And then, as I mentioned just moments ago, because chlorine is electron withdrawing, and that means that chloride is a weak base. That means that chloride is a good leaving group. So the second step for the tetrahedral intermediate collapses is also going to be favorable. So you add all that up, and what does that tell you? It tells you that acid chlorides are going to be very, very reactive. And so when we have a reactivity series for carbonyl compounds, the acid chloride is going to be all the way at the reactive end. Now, how about anhydrides? Because we say, acid chlorides and anhydrides, we kind of, talk about those at the same time. And, if you compare the acid chloride with the anhydride is still reactive, but far less reactive than the acid chloride. Why? Well, for all the same reasons. That you have an acetate or a propionate or benzoate as your leaving group, and this is a much weaker base, i.e. poorer leaving group than chloride. You know that because of the huge difference in pKa's between the HCl and the carboxylic acid. And so this is not nearly as good a leaving group, and the anhydride is to some extent resonance stabilized, certainly more so than the acid chloride, because this resonance structure is certainly better than that one. And so there is some of this, but it's not an important resonance stabilizing form. So the bottom line is that acid chlorides and anhydrides are going to be reactive, and then all the way at the unreactive end are amides and even more so nitriles. And then esters and carboxylic acids are kind of in the middle. So for nitriles, we're going to see very few additions under mild conditions. So if you want to do anything to a nitrile, you really have to use forcing conditions because the nitrile is so stable. And so what that tells you is that you can do selective chemistry on the other carbonyl groups in the presence of a nitrile very often, which can be useful. So the reasons are, I don't need to go through this, all the same reason really. It has to do with electronegativity of the nitrogen versus the oxygen. So now let's take a look at some reactions. There's a general rule that I want you to kind of keep in mind, but also understand, and that is that you can always go, so you can convert more reactive to less reactive. Now this is true in general, but it's definitely true here for the carbonyls. What does that mean? Well, it means that if I have an acid chloride, that's the most reactive of all of those carbonyl groups that we've talked about. And so from the acid chloride, I can make just about anything I want. I can make an anhydride, less reactive. I can make an acid, less reactive. I can make an ester, less reactive. I can make an amide, and there's a way to go directly to a nitrile from here. So in other words, this can act as the starting material for all of them. Now, if I start out with an anhydride, I can go from here to an acid, an ester, an amide, and so on, but I can't go to an acid chloride because acid chloride is more reactive. Okay? So that's what I meant by the more reactive species can always be converted to the less reactive ones. So keep that in mind. Now, let's take a look at acid chlorides. And since they are so reactive, it makes sense that these are going to be the most useful of the acyl derivatives. They're going to be the most useful because we can use the acid chloride to make anything we want. And so they can be, because acid chlorides are the most reactive, they can be used to prepare all of the others. And so let's try ammonia. And you just take the acid chloride and you can dissolve it in concentrated ammonium hydroxide. And so the ammonia, which is in equilibrium with water, attacks the carbonyl. You form this tetrahedral intermediate that spits out chloride, Cl minus. So here I'll show that in the second step. So the tetrahedral intermediate spits out chloride. Chloride's a better leading group than NH3. And that proton transfer takes place. You get the amide and ammonium chloride. Now, notice that I've used up, for every molecule of acid chloride, I've used up 2 ammonias. One ammonia atom, one ammonia molecule ends up here as the amide. The other one, however, reacts in an acid-base reaction to get this ammonium chloride. So I have one acyl group, 2 amines, 2 nitrogens. Now that's okay with ammonia, because ammonia is cheap. And so I can get concentrated ammonium chloride. I can use an excess of the ammonium chloride, no problem. However, if I want to make an amide of a expensive or scarce amine, then this isn't going to be too good, right? Because I'm going to end up chewing up half of my amine just as a base, and only half of it is going to end up forming the amide that I want. And so there has to be a way around that. Now, it turns out there are 2 ways around it. And so if you want your amine to act 100% all of the amine to act as a nucleophile, then what that means is you have to add an auxiliary base. And the auxiliary base has to be cheap and available, and it's there to scavenge the acid. What do I mean by scavenge the acid? Well, this is what I mean. I mean the auxiliary base that you add has to pull off that proton and get converted to an ammonium salt. Now you think about that and say, well, okay, if I have two amines, then that means I'm going to get a mixture of products, because one amine is going to give me this, and then the other amine is going to give me same left-hand piece but different amine. And that is true if you use ammonia, if you use a primary amine, or if you use a secondary amine. But remember, if you use a tertiary amine, those cannot form amides. They can't form amides because, why? Well, because they don't have any hydrogens bonded to the nitrogen. And so the tertiary amine that is cheap and available is pyridine. This doesn't form an amide. If it did, it would form this. So if I have an acid chloride, and I allow that, let's just do it down here. If I have an acid chloride, and I allow that to react with pyridine, what's going to happen? Well, I'm going to get, obviously, a tetrahedral intermediate. And after that tetrahedral intermediate collapses, I'm going to end up with something that is really very reactive. Now, why is this really reactive? That's not something you're going to be able to isolate. How come that's reactive? Well, because you have a positively charged nitrogen bonded to a carbonyl group that has a partial positive charge, so all of a sudden, Coulombic problem. Second of all, this is still a very good leaving group. And so guess what? This is a really good species for forming esters or for undergoing hydrolysis. So this thing is not something you can isolate, but you can form this in solution. When you form that, this does an excellent job of transferring that acyl group to any nucleophile you want. And in this case, it transfers the acyl group to that particular nucleophile. And so this species here, when formed, gets attacked by the amine to give you the amide, and after proton transfer, you end up with the pyridinium hydrochloride as the ammonium salt. And so any tertiary amine will work. Triethylamine can work. Disopropyl ethylamine can also be used. Pyridine is the one that probably gets used the most, and it allows you to have a one-to-one stoichiometry of amine to acid chloride. Now, this all makes sense. The next reaction, however, the first time you hear about it, doesn't make sense. And, but it does work. And so we need to understand why. So there's another way to take an acid chloride, convert it into an amide, and then instead of using pyridine as the base, to use hydroxide, sodium hydroxide as the base. And you think about that, wait a minute, that doesn't make any sense at all. That's the short involvement condition. So in other words, what I'm saying is this: I take acid chloride, and I take an amine, let's just make that a primary amine, and I need a base there to suck up the HCl. So I use hydroxide as my base. Now, why does this not make any sense? Well, because, hey, I've got an electron pair here that can react with the carbonyl, but I have electron pairs here that can react with the carbonyl too. So if I take this acid chloride with hydroxide, who's to say that I don't get the carboxylic acid? That should happen pretty quick, right? Because hydroxide is reactive, it's got a negative charge, more reactive than that. So how does this work? It actually does work, but it works under special conditions. And you'll see how this works, because you do it in two phases. So you take the acid chloride, the amine, and then you have an organic solvent that doesn't dissolve in water, and aqueous sodium hydroxide. Now, The reason this works is because you don't have a phase transfer catalyst. Remember we talked about phase transfer catalysis last time in Chem 272? Yeah, we talked about, yeah, okay, I can see you all remember. Okay, so we don't need to talk about phase transfer catalysis again, but let's just talk about why this works. So you have an aqueous phase that has the hydroxide. You have an organic phase that has the organic acid chloride and the amine. But the acid chloride doesn't dissolve in water, and the hydroxide doesn't dissolve in the organic solvent. So the only place where the two meet, the two reactive species can meet, is at the interface, the water-organic interface. And that turns out not to provide a very effective means of getting the two to react, because they're always in separate phases. And so, because this is a two-phase reaction, this takes place in the organic phase. Once you end up with the ammonium salt, because you will end up with the ammonium salt, now the ammonium salt has a positively charged nitrogen and a negatively charged chloride. That ammonium salt is water soluble. So that can go into the water where it gets neutralized by hydroxide, and then the amine has solubility in the organic phase, and so the reaction proceeds. This is an easy reaction to do. In fact, formation of acetanilide, which is just the acetate of aniline, used to be a Chem 272 or 273 experiment under these conditions. It works very, very easily. The reason is because the hydroxide just doesn't migrate to the organic solvent. Now, if we had a phase transfer catalyst, then all bets are off. What is a phase transfer catalyst? Just what it sounds like. It's a catalyst that can allow something like hydroxide, which is not soluble in organic solvents, to become soluble in organic solvents. So sodium hydroxide, not soluble in organic solvents, but this hydroxide tetrabutyl ammonium hydroxide, this is going to be soluble in organic solvents. Why? Well, because look, you've got these lipophilic groups on nitrogen. These are all going to be organic soluble. So this is going to go into so the cation goes into the organic phase, and because it's a cation, it has to drag its anion with it. And so this species is a organic soluble form of hydroxide. So if I add a little bit of this to the Schotten-Baumann conditions, then the reaction ain't going to work, so you don't do that. But for many reactions, having a phase transfer catalyst is a good way to accelerate it. So talked about that. You can go look up in the index phase transfer catalysis and refresh your memories if you so desire. Okay, so to sum up, under the conditions of the Schotten-Baumann conditions, any reaction, any hydrolysis of the acid chloride by hydroxide, it's a minimum, it's a small side reaction. It's very slow because hydroxide is in the aqueous phase, this is in the organic phase. They only meet at the interface, and that really does not provide an effective reaction medium. Now, acid chlorides will react with all kinds of alcohols and also phenols, and they will react to form esters that are maybe not so easy to make using the Fischer esterification, which is what we learned, right? Fischer esterification is carboxylic acid, alcohol, alcohol in excess, acid catalyst, and then the Chapelier's principle, remove water to drive the equilibrium. Well, for some alcohols, that doesn't work very well. For example, phenols, because they're not particularly nucleophilic, and so those conditions don't work very well. But they will react with acid chlorides, and they'll give aryl esters or phenolic esters. And tertiary alcohols, which will react with acid, also can be used with acid chlorides to form T-butyl esters. Now, to form a T-butyl ester, there's another way. your book, I think, says they can't be made any other way or something like that. Actually, there's a very easy way to make these. And the way you make them is doing it a little differently. You start out with isobutylene and the carboxylic acid. I'm sorry, isobutylene. The carboxylic acid and a strong acid catalyst. And that will give you the t-butyl ester. How does that work? Somebody tell me. How does this reaction work? What's the first step? Come again? Louder. The acid reacts with the pi bond. Yeah, exactly. So what happens is this. This happens in the first step, correct? And that gives you a t-butyl cation. A t-butyl cation is a really good electrophile, right? And this reaction is reversible, by the way, but who cares? Because as soon as at some point, this t-butyl cation gets attacked by this electron pair, that gives you that. And then loss of that proton gives you the product. How did I know that it was this electron pair that attacked it? Doesn't it make a lot more sense to have one of the electron pairs of this oxygen attack the cation? No, why not? Because this is resonance stabilized, and if it's one of these, then the product is not. So remember that. Okay? So let me say that again. This electron pair is the nucleophilic one because the product is resonance stabilized. Okay, so getting back to that. So acid chlorides, very, very useful. We can use those to make any kind of acyl derivative we want because that's the most reactive of the acyl derivatives. Now, acid chlorides, not carboxylic acid chlorides, but sulfonic acid chlorides is something we've seen before. We've seen toluene sulfonyl chloride. This is more or less the same kind of reaction. You have an alcohol, you have the tosyl chloride, you have some other base, and that allows you to make the tosylates. Remember that the tosylates were good leaving groups because toluene sulfonic acid is a strong acid, which means the conjugate base is a weak base, which means tosyl O- is a good leaving group. So this is a way to convert a very bad leaving group, OH, into a very good leaving group. So we do SN2 chemistry right there. So remember that. That's something we've talked about way back when. Also, remember that acid chlorides are more reactive than anhydrides, which means that you can use an acid chloride to form an anhydride. And the way you do that is you take the sodium salt with carboxylic acid, and you can use that to form mixed anhydrides if you want. So this is a way to get around. So this is a way to avoid making every possible combination. If I started with the two carboxylic acids and treated those with phosphorus pentoxide, the normal dehydrating agent, then I'll get a whole combination. I'll get the symmetrical one, the other symmetrical one, and the unsymmetrical one. And so, but if I do it this way, this acts as a nucleophile, that acts as an electrophile. There's no way to get the symmetrical case. So this is what you get. Now, anhydrides can react pretty much the same way as acid chlorides, but slower. And they're less reactive. And one thing to remember, when you use an anhydride, only one of the acyl groups transfers, right? The other acyl group ends up as acetic anhydride, it's acetate, it's the leaving group. So you only use up half of your acyl group. So if I take morphine, for example, and I acetylate these two alcohols, then with acetic anhydride and sodium acetate, then I end up with acetic acid. That's from one of these. And so the left-hand piece ends up here, the right-hand piece, if you will, ends up as acetic acid. This is not balanced, I know that. Diacetylmorphine is heroin. And as you may know, actually heroin is the prodrug for morphine. So when people inject heroin, this gets converted to morphine, and it's this that gives them the high. Okay? So heroin is actually more bioavailable than morphine, and that's why this works as well as it does. So in countries that are less puritanical than the United States, people with terminal disease who have a lot of pain, cancer for example, are allowed the comfort of heroin. Here we use morphine, which works. This works better. I mean, why do you worry? Someone's got a few weeks to live, why do you worry about addiction potential? It's mystifying to me. There was a movie some years ago, many years ago, The French Connection. How many people have seen that? Oh, you have, good. So, yeah, so The French Connection, yeah, so basically, morphine-based, grown in those days primarily in Turkey and other parts of the Middle East, was smuggled to Marseille in southern France, where organized crime converted it into heroin. And in the labs where they did that, they had a waste stream which had a lot of acetic acid in it. And so detection of that acetic acid in the sewer system led them to the labs where this chemistry was being done. Okay, so heroin is just a diester of morphine. Now, esters are not the most reactive acyl derivative, as you know. I mean, acid chlorides and anhydrides. On the other hand, esters are still more reactive than what? They're more reactive than amides. So I can take an ester, and I can take an amine, in this case, ammonia, and I can heat these up, and less stable goes to more stable. And so this chemistry works really well. Now, there's another reaction that esters undergo that seems a little bit mystifying. It's called a transesterification. What does that mean? Well, it means I go from one ester to another. And so you say, but each one of those esters has roughly identical energy. So I mean, in this reaction, it kind of makes sense because higher in energy, lower in energy. This reaction, you say, well, gosh, it's an ester and an ester. These have roughly the same energy. What drives this equilibrium? What drives the equilibrium is an excess of the nucleophile. And so you use the Chatelier's principle to push this equilibrium from left to right. So how big an excess? Oh, I don't know. You need at least 10 equivalents. And so as long as this stuff is cheap, you can do these transesterifications fairly easily. Very often, a transesterification is an undesired side reaction. And so if you have an ester and you have an excess of alcohol and maybe a little bit of acid or base, very often you see this transesterification when you don't really want to. That can happen. Okay, so let's talk about other reactions now. And reduction is one reaction that all of these acyl derivatives undergo. So if I take an ester and I reduce it, first of all, I need a reducing agent that will take an ester down to an alcohol. That means sodium borohydride in general, no good. Sodium borohydride is a mild reducing agent, good for ketones, good for aldehydes, will reduce acid chlorides too, actually, but esters very slow to react. So typically, lithium aluminum hydride. Now, both pieces of this molecule end up as alcohols. So I reduce this CO double bond all the way to a methylene, and I end up with also the right-hand piece as an alcohol. So you get two alcohols from this reduction. They don't have to be the same alcohol, right? They can be different ones. And so now we need to think about what the mechanism is. Well, let's try to think about it before I show it to you. Lithium aluminum hydride. What does hydride mean? It means H minus. So this is, although we don't have a free H minus, the reduction of sodium borohydride, lithium aluminum hydride, always looks as if you have a free hydride. So we're going to pretend, for the purpose of just understanding the mechanism, that we have a free hydride. And it's in quotation marks because you know that it's not a free hydride, it's bonded to the aluminum. But it behaves like so. So hydride attaches itself to the carbonyl, and then that tetrahedral intermediate collapses. So there's one alcohol after protonation. But look what it collapsed to. It collapsed to an aldehyde. The aldehyde is more reactive than the ester. And because it's more reactive, the second reduction with hydride is even faster than the first. And so you never accumulate that aldehyde. That aldehyde decomposes or gets reduced at a faster rate than the ester. It never accumulates. And so that's why I end up with one alcohol from this piece and one alcohol from that piece. So this is what I said before. Sodium borohydride, much less reactive than LAH, does not reduce esters. And that's maybe not completely accurate. It actually will reduce some esters, but very slowly, much more slowly than LAH. And typically, it's not a particularly useful reaction. So if you want to reduce an ester to the alcohols, you use lithium aluminum hydride. Okay, now amides. Well, amides are more stable than esters. And so, but they undergo reduction with lithium aluminum hydride. However, the kind of product you get seems at first a little different. Let me explain. So let's take a look at the ester again. Okay, so in fact, let's use color. So I have an ester here, OR prime, right? I treat this with lithium aluminum hydride, and it says we use color, but it didn't. So I end up with two alcohols, and in fact, I have cleaved that bond, right? That bond is no longer there. The left-hand piece is here, the right-hand piece is there. That's two different molecules. Now we do the same thing with an amide. Same lithium aluminum hydride. Now, what I end up with is one molecule. And you'll notice that this bond is present in the starting material and in the product. Not quite the same. Okay, so there's a difference between these two. Now, the difference is actually not hard to understand because of the mechanism, which is why we always discuss mechanism. So, to recap, there's my amide, lithium aluminum hydride ether, and then I have to treat this with acid followed by base and workup, and there's my product, and the CN bond is not cleaved. In esters it is, the CO bond is cleaved, but in amides it is not. So it must be that the reduction of the amides proceeds by a slightly different mechanism than the reduction of esters. So what might that be? Okay, so first of all, they're kind of weird lookup. You say, well, gosh, why do you have to work up with acid and then base? Here's why. So you need to kill off the lithium and aluminum salts with aqueous acid. But because your product is an amine, then you end up protonating the amine. So you end up getting the ammonium ions. Those ammonium ions need to be then converted back to the amine, and that's why you treat the ammonium ion with hydroxide in the second workup step. And so the first workup step, the acid kills off the reagent and the salts, makes them into water-soluble salts, and then the hydroxide reconstitutes the amine. Okay, so how does that work? Well, if you have an NH group, then, and by the way, the NH group is not necessary for the reduction, and we can talk about that. But if there is an NH group, you get an acid-base reaction quickly. Lithium aluminum hydride is strongly basic, and so that H minus reacts with the NH to give you hydrogen gas, and to give you a salt. It kind of looks like an enolate. And it also generates alane. ALH3 is alane, like borate alane. And base acid. And now, notice that I have a hydride again. I have an aluminum hydride. So the aluminum has a formal negative charge. That hydride gets transferred to the CN bond. to give me this species. Now, I want you to look at this species. Look, focus on this carbon atom. This carbon atom is bonded to a nitrogen and an oxygen. What did we say about carbon atoms like that? We said that carbon atoms that are bonded to either two oxygens or two nitrogens or nitrogen and an oxygen are the equivalent of an aldehyde. So the fact that this undergoes a further reduction should not come as a complete surprise. And so electron pair on the nitrogen can eject this whole piece, and then hydride can attack again, and then with acid you end up with the ammonium salt. So this is a little bit more complicated than the other mechanisms that we've seen, but the key to why you get a different product is because the nitrogen, because of the stability of this imine. This looks like the salt of an amidic acid, which it is. Remember we talked about amidic acids? An amidic acid is this stuff here. This can be an R. So the salt of an amidic acid is this stuff there. And the stability of the CN bond means that this decomposes to give you an imine, which then undergoes reduction. That can't happen with the ester, and that's why you end up cleaving the CO bond. So take a look at this mechanism at your leisure later on, and make sure that the steps make sense. Try to reproduce it. It's not really that much different from any of the others, except for this step here. Okay, this is a little bit different. So to recap then, reduction of esters gives rise to two alcohols. Reduction of amides gives rise to a single amine. And so the reduction of nitriles, which are in a sense related to amides, also gives rise to a single amine. And the mechanism for the reduction of nitriles using LAH, lithium aluminum hydride, is essentially the same as the one we just talked about. So the first step is probably a Lewis acid base reaction to activate the amide. Hydride attacks. Now you have something that looks like an imine, and then again base acid, hydride attack, and there at this point you reduce the nitrile down to the amine. So this is a strange species. I guess I should point that out. The nitrogen here is bonded to two different metals. And usually when that happens, you end up with something that's similar to a carbene. But what this tells you is that this is going to be extremely reactive with water. So any water because it's as if this nitrogen has two negative charges, right? And so this is going to be a very reactive species with water, and it decomposes rather easily. Now this is not the only way to take a nitrile and convert it into an amine. The other way to do that is by catalytic hydrogenation. And remember that carbon-carbon double bonds and carbon-carbon triple bonds can be hydrogenated using hydrogen gas and typically palladium or platinum on carbon as a catalyst. Well, guess what? Carbon-nitrogen triple bonds and carbon-nitrogen double bonds can also be hydrogenalized. And so in this case, if you use Raney nickel, remember, is that very finely divided nickel metal that's used as a hydrogenation catalyst. Use Raney nickel, you need to use fairly brutal conditions. High temperature and 2,000 psi of hydrogen gas. And the hydrogenation takes place in two steps. So one molecule of nitrile soaks up one molecule of hydrogen to give an imine, and then in a faster second step, the imine soaks up a second H2 and gives you the amine. This is, of course, a clean reaction. You don't have to do any kind of workup except filter off the catalyst. On the other hand, if you're going to use Raney nickel, you better have a pressure reactor to get up to 2000 psi with hydrogen. So lots of ways to do that reduction. There are other catalysts that work under milder conditions too. We don't need to talk about those. Now, acid chlorides can undergo reduction too. And acid chlorides are kind of interesting because, so you can do just about anything for an acid chloride. Right? Acid chlorides can be converted to just about anything, including aldehydes in one step. So you can do a partial hydrogenation of the acid chloride and end up with an aldehyde. This is, you don't have to remember these conditions, but what you need to do here to make sure that the aldehyde doesn't go on and get reduced is you have to attenuate the reactivity of the catalyst. So you can make the catalyst less reactive by adding things like sulfur or tertiary amines that are catalyst poisons. These deactivate them. Now, we've seen this trick before. Where did we see this poison catalyst business? Anybody remember? I didn't quite make that out. Yeah, alkynes, correct, yeah. So when we hydrogenated an alkyne to a cis-alkene, a Z-alkene, we used the same trick. And so how it works is kind of a mystery, actually. I mean, exactly what goes on when we add the amine and the sulfur, not well understood. The reason it's not well understood is because this is, again, a heterogeneous reaction. Heterogeneous reactions are reactions that don't take place in solution or in the gas phase, where both reactants are present in the same phase. This is a reaction that takes place in two phases, solution phase and on the surface of the catalyst. And so these are very hard reactions to study as a result. And that's why this is not well understood, because something happens to the surface of the palladium with this that alters the surface of the palladium. And that's why it stops after one reduction. So this doesn't go off and give you benzoic alcohol. Now that we understand chemical reactivity a little bit better, this will make more sense. So I can take lithium aluminum hydride. You already know that lithium aluminum hydride is a strong base, right? Because it reacted with the NH of the amide. And so if it reacts with the NH of the amide, by golly, it's going to react with the OH of an alcohol, which is more acidic. And so I can take LAH and T-butanol in the ratio of 1 to 3. And so this will react as an acid-base reaction. Give you 3 molecules of hydrogen gas that bubbles away. And this new aluminum hydride, where 3 of the 4 hydrogens are now T-butoxy groups, and there's 1 lone red hydrogen, still attached to the aluminum. Now, this is not lithium aluminum hydride. And in fact, it is much less reactive than lithium aluminum hydride. And it is much less reactive because these are big and bulky, and also because the oxygen inductively removes electron density from the aluminum. And so this is so unreactive that it really won't even reduce an aldehyde. But remember that acid chlorides are a lot more reactive than aldehydes, and so it will reduce an acid chloride. And so you can actually take this stuff with an acid chloride and it will stop right there. It stops here because this is just not reactive enough to take this down to the alcohol. So this is another way to go from the acid chloride to the aldehyde. One way is with the Rosenmund reduction, this poison palladium catalyst. The other way is with the very hindered, unreactive lithium tributoxy aluminum hydride. Notice that the reaction is done at cryogenic temperature, -78, dry ice temperature. So the reaction with the acid chloride, even at -78, is fast. But even at room temperature, the reaction of this plus that is really very, very slow. So essentially it doesn't compete. So that seems like a lot to remember. But the thing you really want to remember is not so much that, but this. And so you want to remember the reactivity series and the reason behind it for the carbonyls. Because if you know that, then the rest of it makes sense. If you don't know this, the rest of it doesn't make sense. And so acid chlorides, as we always say, at the high end of the reactivity. And I could put anhydrides here too. I kind of left those out, I guess. Then comes aldehydes, then ketones, then esters and acids, amides, and then nitriles all the way at the unreactive end of the scale. Most reactive acid chlorides and hydrides in here, aldehyde, ketone, and then the rest. So that means that going from the acid chloride to the aldehyde, as we just saw, kind of makes sense. Because I start with a reactive acyl compound, I go to a less reactive one. And I can go from here to there, or there, or there, or there. We've already talked about this. Okay, so you saw the addition of H minus as a nucleophile to an ester. But another very strong nucleophile is what? It's a Grignard reagent or an alkyl lithium. And those are going to be carbon nucleophiles, right? And so we think of methyl Grignard as being methyl minus, right? And so I can think of methyl minus attacking that carbonyl to give me this tetrahedral intermediate, which can then collapse. But now I have a ketone. Ketones are more reactive than esters. And so if this reacts at some rate with the ester, this will react even faster with the ketone. And so I will end up with this tertiary alcohol in which two of the groups are identical. And so here's something you need to be able to do to recognize in the reverse direction. If you see a tertiary alcohol and two of the groups are identical, as they are in this example, I want the light bulb to go off in your head and you say, aha, I could have made that by a Grignard addition to the appropriate ester. Okay? And then you need to remember that yes, esters are reactive, but ketones are more reactive, so that's why this thing works. The ketone intermediate never accumulates. You say that, but I can figure out a way to make this accumulate. Because what I'm going to do is I'm going to use an excess of this and a little bit of that, and then I'm going to add this to the big excess. And yeah, you can play games like that. They don't work very well because there's a big difference in rate between those two carbonyl compounds. So even if you use a 1-to-1 ratio here, what you end up getting is this an unreacted starting material. And so that kind of makes sense. Now, so I just recapitulate that here. Now, if the reaction of an ester with Grignard is fast, what can we say about the reaction of acid chloride with Grignard? Well, it's faster because acid chlorides are more reactive than esters. That's right. And so you can do the same thing with an acid chloride. However, the ketone is still likely to undergo further reaction of the Grignard. And so this is not the preferred way of going from an acid chloride to a ketone. The preferred way of doing it is with the reagent we've seen before, and that's a cuprate. Now, that 8 complex, ATE, when we say 8, what does that tell us? It tells us that the metal has a negative, formal negative charge. And so when we say lithium dialkyl cuprate 8, it means that, look at this, that we have R2 copper lithium. You think of this as being copper R minus lithium plus. Okay, so the 8 tells us that the copper has a negative charge. Now you look at that and say, that doesn't make sense. Copper is electropositive compared to carbon. And so why should there be a negative charge on a metal that's electropositive when we have carbon atoms here? And you're absolutely right. This is a formal negative charge, which means that for purposes of just not losing the charge, you say, oh, well, this is negatively charged. But actually, if you did an electron distribution map, you find that the negative charge is on the carbons primarily, and not so much on the copper. Now, what does that mean? Well, it means that these R groups are negatively charged, and therefore are likely to be nucleophilic. And so if I allow an acid chloride to react with a cuprate, I end up transferring one of the R groups from the cuprate to the acid chloride to get the ketone and a copper species. This is not reactive enough to transfer an alkyl group there, and so it stops at the ketone. So if you want to convert an acid chloride to a ketone without getting tertiary alcohol, you use the cuprate, and it stops at that stage. And I will stop here, and I will wish you a happy week.